So, as I said I was going to last week, I'm gonna go check up on Waj. Hey Waj, how you doing?
Oh, hi. We're good. I've been driving for a while, so we're gonna take a little bit of a break now.
And you know where you're going?
Oh, yeah, Steve told me where to go.
What? How did he tell you? Neither of us can understand him.
I meant that he plugged in the coordinates to the GPS in the Warthog.
Oh, you got GPS? That's pretty cool.
Well, it's a futuristic military. You kind of expect that to be a standard feature by this point.
Yeah, I suppose so. But, is there anything else you wanted to talk about?
Nope, we're good. Thanks for stopping by, and we'll see you next week.
Yeah, no problem. And I'll see you next week. Now, for the rest of the video, I'm going to be talking about Euler's formula, which I'll get to right now. Alright, so some of you may remember that a couple months ago, I made a video about this. And you're also probably wondering, well, why am I redoing this? And I'm not redoing this, I'm expanding on it. Because in the original video, I explained what each of these components are, and I explained how to get there from here, which I'm now writing down. So yeah, I explained how to get to here from here, but I didn't explain why this is true, because at the time, I didn't know why it was true. I didn't find out why it was true until recently, so now I'm doing a video about it to explain why this is true. And while you don't have to watch the original video to understand this, I would recommend that if you do want to fully understand why this works, that you watch it after this video. Now, before I continue on, I need to explain that. Now, some of you may be thinking, I know what that is. That's an exclamation point. But this is math, not English. In math, that's called a factorial. And it's not really a number or a variable. The closest thing I'd call it is a formula. Because what you do is you take a number, and then you put it to the factorial. And what that means is that you multiply that number by all previous integers down to and including 1. But keep in mind that multiplying anything by 1 is the same number as you were multiplying it by, so the 1 has no real effect. So in 2 factorial, that would be 2 times 1. Say we have 5 factorial. That is 5 times 4 times 3 times 2 times 1. So that's what the factorial means. Now, the first thing I need to explain to show why Euler's identity is true is I need to expand that. Now, someone, I'm not sure who, figured out that that is the same as 1 plus x squared over 2 factorial plus x to the third over 3 factorial plus x to the fourth over 4 factorial plus x to the fifth over 5 factorial. And that goes on through infinity, increasing each of these segments by 1 and then adding it on to this. And you may be wondering, well, why do we start with 2 and not 1? Well, we do start with 1. It's just that x to the first over 1 factorial, x to the first is the same as x, and 1 factorial is 1, so, that's just x, which, we have. And I don't know why this is necessarily true, and I don't plan on making a video about it in the future, but nevertheless, someone discovered it and proved it, so we can now accept this as true. And what this means is that we can now plug in any number for x up here, and that will give us an answer, and that answer will be the same as the answer from this if we plug in the same x value for here. So this gives us a way to write e to the x without adding a variable exponent. And you can put this in your calculator and check it. Keep in mind, it does go up to infinity, so you're not going to be able to get to the exact same answer as e to the x, but with each added segment, it will get close. And if you do plug it in your calculator, you'll see how it gets really, really close. Now, the next thing I'm going to show is the expansion of cosine of x, which someone also discovered who I also don't know the name of. But it is the same as 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial minus x to the sixth over 6 factorial. And then, continuing on to infinity. Keeping that same pattern of increasing each of these segments by 2, and then alternating positive, negative, plus, minus, starting with positive slash plus, and then continuing on. And you can also plug this in your calculator, but keep in mind that it also goes on to infinity, so you won't be able to write it all but again, with each added segment, it'll get closer to cosine of x. Now, then the last of these expansions that I'm going to show you, who I don't know who created them, but somebody did, is sine of x. And that is the same as x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, and again, continuing on to infinity, keeping the same pattern of starting at, technically, x to the 1st over 1 factorial, and increasing by 2, alternating positive, negative, plus, minus, starting with positive slash plus. And you, like the previous two, can plug this in your calculator, and again, like the previous two, you won't be able to get it exact, because it, again, goes on to infinity, but with each added segment, you can get it closer to sine of x. You've all heard this before. Now, I'm aware that you guys probably noticed the comparison between sine x and cosine x to e to the x. But you'll notice that sine and cosine of x are alternating positive and negative, while e to the x is just positive. And that is where our I comes in. Now what we're going to do is we're going to now put, for x, we're going to have the xi. And that's going to be a little confusing to have x now be ix. But keep in mind that x is any number, so by now having it be ix is I times, whatever the number is. It's a legitimate math thing to do. If you don't quite understand it, just think through it. I'm sure you'll figure it out. But now, so we have e to the ix. And that will give us 1, plus, ix. And that will give us x squared over 2 factorial. Or ix squared over 2 factorial. And that is the same as I squared times x squared, which is, and I squared is negative 1. So that is the same as negative x squared over 2 factorial, which is the same as minus x squared over 2 factorial. And now we have ix cubed over 3 factorial, and that is the same as I cubed times x cubed, and I cubed is I squared times I, and I squared is negative 1, so that is negative I x cubed over 3 factorial. And this pattern of positive I, negative, and then negative I continues on throughout. Again, with these segments increasing on and just keeping this pattern. Now, we essentially have two terms. Imaginary numbers, and then real numbers. And since this is addition, order doesn't matter. 1 plus 2 is the same as 2 plus 1. They both equal 3. Order doesn't matter, so we can add these in any order that we want. So I'm going to switch up the order. So we still have, e to the ix, and then this equals. But then I'm going to clump the real numbers together. So we're going to have, 1 minus x squared over 2 factorial. And, that continuing on, same pattern. And then we're going to add that to the imaginary numbers of, ix minus ix cubed over 3 factorial. That continuing on. So we can essentially clump them into that group. And, again, that's a legitimate math thing to do. Now, these are all imaginary numbers, and they all have something we can take out of them. We can take an I out of them, which is also a legitimate math thing to do. So we now have, I times then all what were the imaginary numbers. Now, you may notice something about these sets that I've split this formula into now. You may notice that 1 minus x squared over 2 factorial, which will continue on, to plus x to the 4th over 4 factorial, minus x to the 6th over 6 factorial, and so on to infinity, looks a lot like cosine of x. And you may also notice that the other expansion here of x minus x to the 3rd over 3 factorial, continuing on to plus x to the 5th over 5 factorial, minus x to the 7th over 7 factorial, and then on to infinity, looks a lot like sine of x. And we have to multiply it by I. And the reason it looks a lot like those is because it is those. So, e to the ix equals that. And that then ties in perfectly to the other video I made a couple months earlier, which, if you want to continue figuring out why this is true, you should watch that now. But yeah, hope you enjoyed it. Hope I answered some questions from the previous video about this, and see ya!